In this video, we're going to take a look at functions of three input variables. So we can consider multivariate functions where there is one output and two inputs, and we can graph that in three-dimensional space. Now, we're saying we have three inputs and one output, which puts us in four-dimensional space, and therefore it is very difficult to visualize, for our daily experiences are in three dimensions. Now, there is some good news here. Let's take a look at one function in particular that will help us kind of conceptualize why this is important. So here we're looking at a function whose output is the temperature in degrees Fahrenheit at some point x, y, z. So somewhere in three-dimensional space, we can measure a temperature, right? So we have three inputs. We need to know how far east-west, how far north-south, and how far up-down we are relative to some heat source. So the heat source is located at 0, 0, 0. And we want to be able to, at any point in space, if I were to look in a room and I were to, think about this as my room, here's my three-dimensional space, here's the corner of my room, and I wanted, let's say arbitrarily, I wanted to pick kind of some point maybe that's floating up in space right here. I wanted to take my temperature gauge, my thermometer, and I wanted to measure what's the temperature at that point right there. Well, that's four quantities that I've measured, right? I had to measure how far I needed to go this way, I needed to go this way, and I also needed to go up. So that required three inputs in order to get one output. Okay, so I can't visualize this, right? Because it requires a fourth dimension. I can plot x, y, and z, and but really the z here is my temperature, right? So it's a little bit confusing. But here's what I can do. I can actually fix the value of one of the variables and look at the covariation among the other three. Okay, so what I'm going to do is, so we want to study the temperature. There are three input variables, one output variable. So let's take a look at an applet to see how we might visualize this. All right, so here is my little applet to visualize this process. And so here we have the function 200 minus x squared minus y squared minus z squared equals, and in this case, the temperature is the quantity we're going to fix. All right, so right now, the reason this is reading 0 over here is because, for one, I want to, I don't know why the squared is on there, but the reason this is reading 0 is because I have the temperature, the output of this function, set to 0. Now, if you'll recall, we had t on the left-hand side, now the equal sign, and the temperature's on the right. But nonetheless, this is the same function. Let's take just a brief moment to think about what's happening here. So if I'm at the heat source, which is located at the origin, then that's going to be the hottest point. And I can see that if I take away from 200, 0 squared, and then I take away 0 squared, I take away 0 squared, then my temperature right at the origin is the hottest point. That's the 200. But as I increase x and or y and or z, we see that we're subtracting off from that 200. So, in reality, the farther we get away from the heat source, the cooler it's going to get. Now, here's another representation of this. So what this actually shows is the same equation, but manipulated. So x, y, and z are all on the same side, and then the constant is moved to the other side. And what I want to point out here is that in two dimensions, we know a circle is of the form x squared plus y squared equals radius squared. In three dimensions, we have a three-dimensional circle is called a sphere. And, you can talk about plot a circle in 3D too, but the three-dimensional version of a circle is often what we think of as a sphere. And notice that the formula looks almost identical, except it has the square of all three components, the x, y, and the z, equals, and then the radius squared here. So the radius right now is actually, of this sphere, is 14.14, because that is the square root of 200, and the square root of 200 squared is obviously 200. Okay, so what's going to happen here? Well, I can change the temperature, and as I change the temperature, I see that the size of the sphere is changing, right? And what is this telling me? Well, I am altering the temperature, and every single point along the sphere tells me where the temperature is exactly 0. So if I set this temperature really high, right, why does the sphere get smaller? Well, the sphere gets smaller because in order to find the location or the regions where the temperature is 180 degrees, my heat source is right in the center, right there, right? And the closer I am to that heat source, every radially along this sphere, right, in all directions, the heat source kind of emanates equally, assuming there's no walls or anything like that between it. So I have to be really close in order to get that fixed temperature of 180. And we see here that what happens is I'm changing the temperature here. When I subtract over the 200, I'm making this number smaller, meaning as I increase temperature, the radius of my sphere gets smaller. Okay, and as I decrease the temperature, well, in order to get a lower temperature, I've got to go farther out, right? So now I'm actually making the temperature smaller. I'm subtracting away over 200. My radius becomes bigger, so now I have to be 7.72 meters away, or feet, I think, from the heat source in order to get a temperature of 140.4 degrees. So this is one way we can study multivariate functions that have 3 input variables and 1 output. We can still up to 4 dimensions, we can fix the output variable in 4 dimensions, make it a 3-dimensional problem. And now, of course, I could even take cross sections, but you know, in this context, it doesn't make a whole lot of sense because x, y, and z just represent locations in 3-dimensional space. And that's probably the extent to which we need to consider this right now. So let me hop back over to the lesson. So what we've established is that we conclude that to get to a lower temperature, you must move radially, right, as a radius from the center. You must move farther away from the heat source in any direction, really, as long as you're moving away from the origin, which is where the heat source is located. All right, so that's kind of the idea of plotting. Again, it gets obviously more complicated, more sophisticated, but really what we're doing is we're just changing the 3-dimensional shape every time we fix the value of the output variable. In this case, the output variable is temperature. Here's just kind of a summary of what we saw. Once again, the higher temperature occurred closer to the heat source, which is right there. The lower temperature occurred, you know, we had to go a lot farther out to reach that. Here, we didn't have to go out quite as far. Oh, I don't know what's happening there. So if we want a lower temperature, we got to go farther away from the heat source. All right. We can also talk about these kinds of functions. So let's just say for a second that, again, I have 1 output, I have 3 inputs here. B, the output, is my blood pressure, and I'm not going to give it units now because that's not really important, is a function of the amount of coffee you drink, right? So maybe that's measured in number of cups or ounces or whatever. C, the number of times you exercise, maybe that's per week, etc. We're going to represent that by X, and the amount of stress you encounter each day, S. And we have some questions about this. So what do we think? Well, without being provided the actual equation that generates blood pressure as a function of these 3 quantities, we want to know, is B an increasing or decreasing function of C? So what are we asking? Well, what happens to blood pressure as you increase the amount of coffee you drink? Well, in all likelihood, this isn't 100% accurate. The idea is just to give us some intuition about this. As you drink more coffee, blood pressure likely increases, right? The more coffee you drink, the more caffeine you have. We know that adversely affects blood pressure in many situations. Okay, so that's an increasing function. So as C increases, B increases. Is B an increasing or decreasing function of X? So what are we asking? We're saying, if as you exercise more, what happens to your blood pressure? Well, ideally, in an ideal setting, exercise helps reduce your blood pressure, helps to normalize it. So we'll just argue here, the more you exercise, the lower or more normal your blood pressure is. And finally, we're going to ask, so that's a decreasing function. As X increases, B decreases, right? The lower your blood pressure is. Here was an increasing function. And finally, is B an increasing or decreasing function of S? Well, the more stress you encounter, the more stressed out you are, and probably the higher your blood pressure is as a result of that, maybe that fight or flight reaction. So we're going to say here, or I'm going to argue that the more stress you have, the higher your blood pressure is, and therefore that implies that this is an increasing function. So the goal of this video is just to give kind of an overview of, well, what do we do when we have more than 2 input variables, i.e. we have 3 inputs and 1 output. And this is about as far as we can take it in terms of visualizing. Now we can obviously operate with equations that have many input variables, and in fact even many output variables potentially, but the visualization component is sort of lost. So we can still do calculus on these types of functions, and we will. We can still address obviously questions of how the output is affected by each of the inputs. And oh, by the way, here we're just assuming that if we're changing C, we're holding everything else constant, right? That same principle still holds. You can't say, well, what happens when you increase C, but you decrease X and increase S? That's difficult to say. We've still got to take on the attitude of we can only adjust or tweak one dial at a time and see how the quality of sound, so to speak, changes. But when we start changing dials together, obviously one may cancel out the effects of the other. So that's it for this video. Hopefully it's been helpful.